Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for talented high school students. In this video, I want to tell you about how you can manipulate power series in certain fundamental ways which are very useful for computations. So what we'll do is we'll start with two power series and we'll assume that they're both real just for simplicity. So in other words, they have real coefficients. The first one will be this a of x, which is a0 plus a1x plus a2x squared and so forth. We're going to assume that we have some radius of convergence. So if you look at the limit of the absolute values of the ratios of consecutive terms like this, you'll get Ra. So that gives you absolute convergence in this open interval from minus Ra to Ra. So that means the interval of all real numbers strictly between minus Ra and Ra. I will have another power series which is similar, b of x, and that also converges absolutely because we'll assume we have this limit of the absolute values of the ratios of the coefficients equals to this Rb, and of course one of these radii will be smaller than the other, or at most the size of the other. So let's suppose this Rb is the smaller of the two. Okay, so we'll have absolute convergence of this power series whenever the value of x has absolute value less than Rb. Okay, so in this interval, open interval from minus Rb to Rb. Now, what types of things can you do to these power series? So the first thing that you can do is you can take this sequence of coefficients and you can multiply all those coefficients by some fixed scalar lambda. Okay, and that will give you a new power series. And you might think, well, what is the value of this? And I hope you can guess what the answer is. It's going to be exactly the same as the original power series, a of x times this scalar lambda. And that's going to hold for which values of x? For every single x for which the original converges. So on this open interval from minus Ra to a, so where the absolute value of x is less than Ra. So another thing that you can do is you can combine these two power series together. And there are two ways to do that. The first one is to add the two. So what happens when you add the two? So that means that you just add them in the way you would expect by adding polynomials. Normally what you do is you just add corresponding coefficients. So we're going to do the same thing here, okay? So we're going to get a new power series from these two. And the new power series is going to have for the coefficient x to the n, just an plus bn. So the coefficient of this ax at x to the n and the coefficient of x to the n in bx, we just sum them together, okay? And that gives us a new power series. And you would hope that the value of this for all x, okay, for which this converges, is going to be a of x plus b of x. And certainly when you know this is true, remember this converges on here, this one converges on the interval from minus Ra to Ra, and this converges on the possibly smaller interval from minus Rb to Rb. So on the smaller interval at least, you do actually have this equality, which is a rather nice fact. This is actually quite easy to prove, and you can prove it on the activity sheet that's associated to this video here. Another thing that you can do is you can multiply a of x and b of x just using the Cauchy product. So that gives us a new power series. And what's the new power series? Okay, so if you take the Cauchy product of these two, okay, you will see that the nth term, that corresponds to the term which has x to the n in it. And what's the coefficient? The coefficient is given by what you see in the Cauchy product formula. Okay, so the coefficient of xn is you multiply coefficients of a's and b's, so ai times b n minus I. Okay, so the sum of these subscripts is equal to n, and that will give you the coefficient of x to the n, okay, when you sum all of those up. And again, what happens is you would like this to equal a of x times b of x, and that's true whenever x is in the interval where both of these are defined and absolutely convergent, so on the open interval from minus Rb to Rb. And the final thing that you might want to do with a power series is, well, this is going to give you a function, this a of x. Okay, you can ask, well, is it continuous? Is it differentiable? And if it's differentiable, is it actually a differentiable function whose derivative you can write as a power series as well? And the answer is yes. Okay, so in this case you can differentiate it on this open interval where it's absolutely convergent from minus RA to RA. And that is given by this power series here. And it's quite easy to see what the power series is going to be. You just basically differentiate this term by term. So the term an x to the n, the derivative of that is just n times an x to the n minus 1. Okay, and that will give you a convergent power series. And what will it converge to? It will converge to the derivative of this a of x. Okay, so there's quite a bit in there. So let's give a little example which shows how this proposition works. Okay, so let's look at one power series that we know very well. So that's going to be given by 1 plus x squared plus, and this is just a geometric series. And we know how to sum that. That's 1 minus x. And that's on the open interval minus 1 to 1. So we'll always consider us as being in this range here. Okay, so let's see what types of things that we can do. So the first thing we can do is we can differentiate this. Okay, so if we differentiate this, what do we get? So let's just differentiate this left-hand side here, okay, this term here. So 1 goes to 0, that's why you start at n equals 1. The x gives you 1, plus the x squared gives you 2x, and then you get 3x squared, plus dot dot dot. And it equals the derivative on this side here, at least for all x in this range. And what's the derivative of this here? So I guess that's easier enough. You'll find that's 1 on 1 minus x all squared, okay, which turns out to be a of x squared. Okay, so one of the things that you will see is firstly this is differentiable, okay, and the derivative is given by a power series, which is this one here. And that's a nice way actually to work out what this power series is. Okay, if you recognize it's the derivative of this one here, then you can see that, oh, okay, what is this as a function? Okay, it will converge for all values of x in minus 1 to 1, and it will converge to this value here, 1 on 1 minus x all squared. And then you might think, well, this a of x squared, we can also compute this using part C, the Cauchy product. So let's just see how that works, okay? So what's a of x squared equal to? So what you do is you have to multiply 1 plus x squared plus dot 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 with 1 plus x squared plus dot dot dot. And let's just see how you get the same answer. And remember how the way the Cauchy product works. So basically you do term by term products, okay? So you start off with n, so you have 1 times 1, so that's the first term over here. What's the next term? The next term is all the terms that involve x. Okay, so you can get x times 1 and 1 times x. There are 2 of them, so you get plus 2x. Okay, so you get the third term in the Cauchy product. Remember, we have to look at these 3, and basically you have to pair them up, the products, multiply them, and add. So you get 1 times x squared, that's 1x squared, so you get 1x squared there. When you do x times x, you get another x squared, that's a second x squared. And when you do this x squared times this 1, you get the third x squared, so you get 3x squared. And I hope you can see from the pattern that you're going to get exactly the same answer. So this is a wonderful way of showing in 2 different ways what does this power series converge to on this open interval here. It converges to 1 on 1 minus x all squared, and you can get that either by using the fact that you have this formula here, which basically says that if you have a power series like this, you can differentiate term by term. That's how we express this formula here. Also, if you want to multiply 2 power series together, you can take the Cauchy product in this case. And that'll give you a new power series, and it will converge, this will converge, and it will converge to the product of these 2 power series. In this next example, we want to show how power series can be used to study differential equations such as this one here. So here we're looking for a function b of x such that b dx equals b. So hopefully you know the answer to what this function b has to be. But the approach that we'll take is that we'll assume that b of x can be represented by some power series. Okay, so b of x equals the sum from n equals 0 to infinity of b and x to the n. Okay, and what we'll do is we're going to look at this differential equation, and we'll look at it from a power series perspective. Okay, so let's do that. So what we'll do is we'll write both sides as power series. So the left-hand side here is just this power series here. It's the sum from n equals 0 to infinity of b and x to the n. And what's this one here? So this is db dx. And so this here you can get by term differentiation. So let's do term by term differentiation. The n equals 0 term drops out, so we start at n equals 1, go up to infinity, and we differentiate x to the n. You get n times x to the n minus 1, and of course the bn is still there. So it's n times bn to the n minus 1. And it's going to be convenient that we change variables now. So we're going to let n equal m plus 1. So that's what we'll do. So if n equals m plus 1, that means m is 1 smaller than n, so it starts at 0. So what you'll have here is the n here will be m plus 1. You'll have b subscript m plus 1, and this will be x to the n. Okay, so remember, in other words, n equals m plus 1. N equals m plus 1, so this n equals m plus 1, and this n is m plus 1, so you can have m there. And so what's the easiest way to make this hold? Okay, the easiest way to make this hold is the equality of power series. Okay, so this is this implication at least, and in fact it's quite easy to see that both sides you get the other implication as well. The easiest way to make this hold is if you have the coefficients of both power series are the same. So that's what we're going to do. So we're going to assume that the coefficient of x to the n, so we'll put in here now m equals n, bn is equal to n plus 1 bn plus 1. Okay, so let's just see what happens. So it's quite easy to see what happens here. So suppose you start with b0, okay, and then what happens to b1? So remember, another way to write this is that bn plus 1, how is it related to bn? You divide it by n plus 1. So b1 is going to be b0 on b on 1. Okay, so we divide it by 1, so that basically means it equals b0. Okay, b2 is you take this b1, which is also b0, and you divide it now by, well, it's 2 here, so you divide it by 2. b1 on 2 equals half. And b3, what's b3? Well, n plus 1 now is equal to 3. And you take the previous term, which is this half, and you divide by 3. So this is 1 on 2 times 3. And if you continue, I hope you can see that I lost the b1 here. b1, which is also b0. And this is also b0. Yeah. And then if you continue, you see that bn is equal to b0 on n factorial. Okay. So if b0 is equal to 1, then what do we get? We get b of x is equal to the sum from n equals 0 to infinity. You have 1s here for the b0s, so this is just 1 on n factorial x to the n. And in this case here, what's the constant term here? So b of 0 is equal to, well, in this case when n equals 0, 1 on 0 factorial, so this is equal to 1. And so here it looks like we have a solution to this differential equation such that b of 0 is equal to 1. And so we know that the solution to this differential equation, whose value at 0 is 1, is just e to the x. So now we have a new power series, okay, that's this one here, and it turns out that this equals the exponential function here, e to the x. Of course, for this to be true, you probably want to say that, well, this had better be convergent. So note b of x converges absolutely for all x. And why is that true? To check that it's true, I guess you need to check what is its radius convergence. So let's check its radius of convergence. So let's look at the limit as n goes to infinity. And you look at the nth term, which is 1 on n factorial. You divide that by the n plus first term on n plus 1 factorial. Look at the absolute value of that. And that's a limit as n goes to infinity of, well, most of the terms cancel here. And what you'll have is that the only term that doesn't cancel is the n plus 1 on the denominator here. It's in the denominator of the denominator, so that's just n plus 1. And this equals, of course, the limit of this is infinity. It's going off to infinity. And so that tells you that the radius of convergence infinite being, what does that mean? That radius of convergence being infinite, that means that this power series here actually converges for all real values of x. And this is the power series method of trying to solve this differential equation. So I hope from these two examples and from the proposition I gave you, you can also now manipulate power series.